linear classifier, but not just a hyperplane. We want to essentially fit a slab. We want to fit a classifier with a certain margin, right? So you've seen discriminative classification before. You have seen linear classification before. That is a parametric form of a classic perceptron. We've seen perceptrons before, right? Logistic regression. Can someone tell me what logistic regression does, for example? What is the difference between a perceptron and a logistic regression? This was literally like 3 lectures ago, right? Yes?
Logistic regression turns it into a probability.
Right, so logistic regression, you can think of it as a probabilistic classifier, right? Essentially, they both learn linear classifiers, yes? But like many other situations, they'll make some implicit assumptions about the data. So that does not mean that they'll learn the same classifier, the same bound, right? So they are going to make their own implicit assumptions, and based on that, they'll build a classifier. And even if you throw the same data on both of them, they'll both learn a linear classifier, they may differ, right? So now, instead of just learning a classifier, what we want to do is to learn a classifier with some margin. And the reason for this is this is what we talked about last time, right? We were just starting on this. So if, let's assume, it's a very harsh, very strong assumption, saying that the data is separable. In general, you will not see things like that in practice, but let's assume, just for the sake of argument, that it is separable. So if it is separable, then there may exist many linear boundaries that can help us distinguish from y is equal to +1 versus -1, right? And then we were talking about how to choose the best one, and then we essentially settled that because if you choose, for example, this one, it's close to the red triangles, and then if a new data point comes in which is likely to be close to other red data points, then this boundary, this linear classifier may not be a good idea because it's likely to misclassify data points that, new test data points that happen to be close to the training red data points, right? And it's not an unreasonable assumption to make that the new test data point, the distribution of new test data points is close to the distribution of the current training data points that we have, right? So to be able to generalize sort of the best, we will choose something like this, which happens to be far away as possible from both the clusters, from both the class clusters essentially, right? And then also, I guess we'll talk about, all of these, this is what we talk about, right? So this is what an SVM is. SVM is learning not just a linear boundary, it's learning a linear boundary with a margin. So instead of fitting like a sheet of a hyperplane, it will try to fit a thick slab. And it will try to find a slab that is as thick as possible. The thickness of the slab is given by d minus plus d plus. So d minus is the distance of the classifying hyperplane from the negative class, and similarly d plus is the distance of the classifying hyperplane from the positive class. You sum them up, that's your total margin. You want this to be as big as possible while still classifying the training data perfectly, right? As we fit a slab, we'll see that there are some data points that lie at the boundary of the slab. These are called support vectors. If we live in a d-dimensional space, we can show that there will be at least d+1 support vectors. Right? So these data points that lie on the boundary of this thick slab are called support vectors. If there are less than d+1 support vectors, that means you can adjust the boundary and maybe even the thickness of the slab to increase the thickness, for example. Right, so here, is this actually the best one? Or can you make it thicker? So here you only have, you live in two-dimensional space, right? But you only have two support vectors. But I just said that for d is equal, in a d-dimensional space, you should have d plus 1. So is this the thickest boundary, or can you further improve it?
Further.
So how, like for example, if you could like tilt it a little bit and then increase the thickness and then get that top triangle also to be on the boundary. Do you see that intuitively or no? So in general, if you live in a d-dimensional space, you should have at least d plus 1. There can be more than d plus 1, right? For example, if there are some data points which are collinear, and in that case you have more than d plus 1 support vectors. So the support vectors are the ones which lie exactly on the boundary. Yes? Great. So let's talk about hyperplanes and boundaries and how to like actually construct an optimization problem that can help us solve this thickness fitting issue, right? In general, I can write a hyperplane like this. Yes? You've seen, all of you have seen this before. What is W here? Yes? It's a vector, right? So what is that vector in context of what the hyperplane is? Yes.
It's like the weights of each one of the data points.
Right. Yes, that's. I'm saying geometrically, does it have an interpretation?
It's
Yes. At the back.
perpendicular.
Sorry, you raise your hand first. Yeah, I'll come to you also. Yes.
Is it the slope?
Is it the what?
Slope?
The slope. Okay, so you're thinking of it in terms of lines. Yes. Okay. Good. Yes.
It's perpendicular to the hyperplane.
Right. So if this is the hyperplane, W is the vector that's pointing like this. Yes? So if, for example, W lies, if your hyperplane is actually passing through the origin, this is your W. Do you see how all the vectors that lie in this hyperplane will have dot product 0 with W? So this hyperplane is defined as is equal to 0, which means all the vectors x that lie within this hyperplane will have dot product 0 with W, with the perpendicular to this hyperplane. Right? So this is in 2D, you can sort of at least think it in 3D, right? All the directions, so any hyperplane that passes through the origin, all the vectors that have dot product 0, right, will essentially construct that hyperplane. Right? It will mark all possible vectors which have dot product 0 with that. Right? But if you have it equal to some B, then this thing will move left or right. That's sort of a primer to coordinate geometry. You've seen this in high school, just in case you didn't remember. Right? So I can write a hyperplane like this. Yes? So I just said I can translate the hyperplane left or right, which means if I know the equation of the middle hyperplane, I should know the equation of maybe the right hyperplane also, and correspondingly the left hyperplane. So the rightmost hyperplane, right, which is the boundary of the thick slab, is essentially a translation of the middle classified hyperplane. Yes? So that should look something like this. So there should some C, right? So W transpose X plus B is equal to C. And then because this is going to be equal, this is going to be equal to minus C on the left. Agreed? Now here's the claim I'm making. I'm saying I can divide the entire equation by C, all the equations by C, and that does not really change the hyperplanes. So instead of having W transpose X plus B is equal to minus C, I can just replace this C with 1, and that can be done without the loss of generalization. It will still mark the same hyperplane. Do you agree? I'm just dividing both sides with C, right? So that means I can write it like this. Are we on the same page? Right? And now from this, we can directly see that the margin, which is 2d or d plus plus d minus, is just going to be 2 divided by the norm of W. Yes? Is it obvious? Can someone explain why that is the case? People who say it is obvious. It's not super obvious to me. Yes.
The wave vector is perpendicular to the hyperplane.
Right.
So,
Yes.
If you have like that equals -1, then your wave vector is exactly that distance.
The weight vector is exactly this distance?
Or yeah, like if you have that left line is -1, then essentially to go from the middle line to the left line, you go a distance of 1 wave vector.
Right. But this is 2 divided by now.
Yeah, because you have both sides.
Right, but you're dividing it by the norm.
Because you're like scaling it there, so you have to divide it, right?
I see. Okay. Honestly, I'm not able to get your intuition, but you are right. That's essentially the way to think about it. So you're saying you have to go in that direction, right? So let's try to. So let's say you live here, right? This is some point x1, right? So then W transpose x1 plus V is equal to -1. Yes? And like you said, let's go in this direction. How much do we go? 2D, right? What is this direction?
WT.
What direction the band? What is this direction?
WT.
WD?
W to the power T.
W to the power of D.
Or WT transpose is what I'm saying.
W transpose?
Yeah.
Then what?
That's the direction of that vector, right? That's what this direction is.
So the W is this perpendicular direction, like we just talked about, right?
Yeah.
But W is a vector. For direction, what do we need? We don't need the magnitude, we just need the direction, right? Yes.
I think the way I was thinking about it was that you take x1, the closest point on the hyperplane line on the other side. So we have a straight line distance.
Right.
Of, I guess. Well, between. Is it like how many W's we need to get to
Right.
x1 to x2?
Yes. So there is, I'm saying, this is x1, and then from here let's get to x2. So how much do I need to go? That's your question, right? Yeah, I'm asking the same question. So in that direction, what is that direction is my first question. Yes.
Is it W hat, like normalized one?
Right. So W is the vector. To get the direction, first we have to normalize. We'll have to get the unit vector, right? So we need to go, so x2 is equal to W divided by the 2 norm of W, which is the length of W, right? And then I'm gonna add this x1 here. So if I'm at the origin, this is my x1, I'm gonna go in this direction, and that will give me x2, right? That's how you add vectors? Right, so if this is my x1, I go in this direction here with some W, then I get some alpha times W, I get this vector x2, so that means x1 plus alpha times W is equal to x2, right? That's how you add vectors. So now I'm adding vectors. We know the unit direction is this, but how much do we go? So we know the unit direction, we are going in that direction, but how much are we going? Maybe I'm not doing a good job here. Yeah.
Would you be going like 2D?
2D, right?
Yeah.
No? Is it not obvious? Is it the way I go? So I'm going in, this is my x1. I want to go to x2. I know the direction and I know the width, right? So this is d1, d plus, d minus. In general, let's assume d is equal to d plus is equal to d minus, right? Because we want, it ideally we'll have the center classifying hyperplane equidistant from both the data sets, class clusters. So then we are going 2D, right? So this is the magnitude and this is the direction. If I add this to x1, I'll get to x2. Now x2 lives on the rightmost hyperplane, whose equation we also have. It's this, right? And now I can combine these three equations. Essentially, I can plug in the value of x2 from here to here, which gives me W transpose x1 plus 2D W by plus B is equal to plus 1. Yes? If I make a mistake here, that's basically a test for all of you to make sure you guys are following along. There's no mistake here, right? Okay, so now let's try to take this in. So we'll get W transpose x1 plus 2D. What is W transpose into W? D is a scalar, yes.
It would be the norm square.
Norm square. W transpose W is basically the norm square of W, right? Divided by the norm of W. So this thing goes away, right? Yes? And then you have a plus B here, and that's equal to minus 1. So now we have W transpose X plus B plus 2D times the norm of W is equal to plus 1, right? But from the first equation, what is W transpose x1 plus B?
Minus 1.
Is just equal to minus 1, right? So this thing is just equal to minus 1, which means 2D W is equal to 2, right? Or D is equal to 1 by 2 norm of 2. Yes? So that's why the overall margin is 2 divided by W norm. Right? I think that's where your intuition is going somehow. Sorry, I'm not able to fully get it. But we've derived it, and I think this is where you're essentially going to, right? So makes sense. Yes.
Shouldn't it be? Isn't D equal to D positive plus D negative?
Yes. Not plus, equal to. We're saying the individual half
Oh,
width is
okay.
right. So this total thing is 2D.
Cool.
Right? Any doubts here? So what we have done is we have said that we want to find the best W. That's what we're going to optimize for, right? Even in the parametric form of when we were doing logistic regression or when we were doing perceptron or least square laws, you want to find the best W. So we still want to find the best W, but we want to do this while maximizing the margin, right? So that gives us the optimization problem, right? So that's what this is saying. We want to maximize the margin. So to write the optimization problem, and you'll see this coming up in a lot of practical situations also, when you have access to a system and you want to optimize it somehow under some parametric form. The way to do this is write down what is your optimization problem. Like the optimization problem is the whole thing, but what is the maximization or minimization over? So here the maximization is over the margin, which happens to be 2 by W, which we just derived, right? And we want to find a W that not just maximizes the margin, but also classifies all the examples correctly, which means we'll set up something called a constrained optimization problem. So we define what is the optimization criterion first at the top, that is maximization of margin, and then we will add constraints which look like this. So this is the first constraint, right? So if this is my hyperplane, this is my W, then this entire half space will have W transpose X is greater than equal to this is just coordinate linear algebra from high school, right? No? You've never seen this before? So everything here will have positive dot product, everything here will have negative dot product. You've never seen that before? On the hyperplane it will be 0. I mean, yes, there's a B here, sure. You've never seen this before? Every hyperplane divides the entire feature space into two halves, right? So on the hyperplane you'll have W transpose X plus B is equal to 0. All the x's that live here will have greater than 0. All the x's that live there will have less than 0, right? Have you seen this before or no? Because this is something that I'm going to assume. I mean, sure, maybe you forgot a couple of things and I can like talk about them as we go. But the geometric intuition will not settle in if you're not comfortable with these things at least. Okay, so that gives us the idea of how to define the constraints. So this is my first constraint for the positive class. So like I said, everything over here is plus. So we want W transpose X plus B is not just greater than equal to 0. We want to be greater than equal to 1. We want it to satisfy this constraint with some margin. Yes, that's what we said on that hyperplane over there, right? So this hyperplane here has W transpose X plus B is equal to plus 1. If whatever we want, whatever data points that we have, we want them to lie on this side of the rightmost hyperplane, right? Which means we want this thing to be, the constraint to be greater than equal to plus 1. Yes?
Is there a reason why you picked +1 and -1 and not +0.5, +2?
You could do that. The W's and B's, that's the point. So if you pick 0.5, the W's and B's will get rescaled accordingly. You will still pick some, like you'll essentially pick the same thing. Right? Rescalings will not matter. Right? Your margin will get rescaled accordingly. Right? Depending on the constraint. So this is for the positive class, and similarly we have for the negative class that all the green circles should lie towards the left of the leftmost hyperplane. And that is why we have W transpose X plus B less than equal to -1. This has to hold for negative class for all y is equal to -1. This has to hold for the positive class. And we can combine these two constraints together like this. We just multiply with yi in the beginning and say yi W transpose X plus B is greater than equal to 1. It's just a sort of a compact way of writing these two constraints together. If you plug in +1 here, you will recover the first constraint. If you plug in y is equal to -1 here, you will recover the second constraint. Do you see that? So your overall optimization problem now is maximize 2 by w or 1 by w, or you can say minimize w, the length of w, while ensuring that these constraints are satisfied. Let's take like maybe 5-10 seconds here to make sure that it's sinking in. If there are any questions, please ask. Yes.
So I thought the question we're solving is maximizing the distance. D1, D plus D minus.
Right.
If you already set the constants equal to 1 and -1, we
Right.
already like assume that we know.
No. See, that's yeah. Okay. Let's take a step back, right? So we said the middle hyperplane is that W transpose X plus B. You're saying the rightmost are some C and minus C. Right? I'm saying if I set it equal to C is equal to 1 or -1, I'm essentially rescaling all the variables in my equations. See? I'm just rescaling them. This loses no generality. It will still mark up the same hyperplanes because you're just, the degrees of freedom, the number of degrees of freedom is still the same. Right? So when you're setting C is equal to +1 or -1, you're not saying that, if the margin should be 1. There's no difference between this and when you set it equal to 1. The hyperplanes that you construct, the equations of the hyperplanes, the two equations, they'll point to the same hyperplane. Okay, so let's say there are two lines, right? Are these two marking two different lines? Are these equations of two different lines? Same thing. Exactly the same. Right? Or because it's 1 over there, so you set it as 1 and you write 2 by 6, 2 by 6 and then 4 by 6 here. Are these two different lines or the same line? Same line. Exactly the same thing's happening here. Does this help? So by setting it as +1 and -1, all we are doing is we're just still fixing the equations. This is my equations. That gives me what D plus and D minus are. And then we said ideally we want the classifying middle hyperplane to be equidistant from both the classes, which means D is equal to D plus is equal to D minus. And then we derive this thing saying that the margin, which is equal to D, is actually equal to 1 by 2 norm of W. And now we say we write our optimization problem, which is maximization of margin, maximization of 2D, is the same thing as maximization of D, is the same thing as maximization of 1 by W norm, is the same thing as minimization of W norm. Maximization of 1 by something which is positive is the same thing as minimization of that same quantity, right? Which gives me this optimization problem, maximization of margin or minimization of the W norm, subject to the constraint that all the examples are correctly classified with margin. They're not just correctly classified, they're classified with margin. So the positive points lie towards the right of the rightmost hyperplane, and the negative points lie to the left of the leftmost hyperplane. That is what this constraint is capturing. Yes? And this is sort of also the intuition that you'll see here, how, well, it's not exactly the same thing, but you'll see a lot of papers talking about how min-norm solutions are a good idea. This is sort of a precursor to all of these more like recent results that you see in the literature. So here you're not just hunting for max margin solutions, you are just hunting for min-norm solutions. Right? So that is the optimization problem. We'll talk about how to solve this. But let's say you have solved it and you have some W star that you have found, right? Then how do you test? You have 3 hyperplanes now, you have fitted a slab. But at the test time, which hyperplane will you use to actually do the classification? The middle one, right? That makes sense? That's what we were going for. The middle hyperplane is our actual boundary. We are setting up the constraints to fit a slab, which we are saying should be as thick as possible. So that is what where did that go? Oh, this thing at the top is saying. So once you have learned a W, the very first line, once you have learned a W, you find out W transpose for every X that comes in, test data point, you write down W transpose X plus B, and then you check what is its sign. If the sign is positive, it means it's supposed to be here, and then you predict the class to be +1. Right? If the sign is negative, that means the prediction is that it is belonging to the negative class. Great. So let's talk about how to actually solve the SVM problem. So like I said, you can convert the maximization to minimization. It's the same thing. So that's the optimization problem at the top. This is something called a quadratic optimization problem. There are some subclasses of optimization problems that have been separately studied. So for example, we'll talk about convex optimization a little later in the course. I think I'm the one talking about that. Or is it Professor Zhang? I'm not sure. I think I'm the one. So we'll talk about them in a little more depth when we discuss introduction to optimization. So there we'll talk about a subclass of problems which specifically pertain to convex optimization. And then there are subclasses where, for example, we say linear optimization problems. And then there's quadratic optimization problems. The purpose of studying these subclasses separately is that we can focus and derive guarantees and algorithms that help us go deeper and solve these more efficiently, right? So this problem is very well known, and there have been many algorithms that we know try to solve this problem. So this is something that we call a constraint optimization problem, which means there's an optimization function that we want to optimize, subject to some constraints, right? So this is called a constraint optimization problem. What you guys have already seen when you discuss L2 regularization and L1 regularization is something called a regularized optimization problem, right? So instead of having a constraint, which is like a hard constraint, that find me a W that optimizes this function, which is the minimization of norm, subject to these hard constraints. These hard constraints should not be violated. If a W violates any of these constraints, remove that W from consideration. The algorithm will never output a W that violates even one of those constraints. On the other hand, when we talk about regularized problems, people remember L2 regularization, right? So what did we do in L2 regularization? So again, just 2 lectures go, right? So hopefully you all remember it. Yes. Make the parameters as small, right? So there we said that. So if X is your data matrix, you said find me a W that fits the data well, while at the same time make W as small as possible. And then this is minimization over W. So W here is my parameter. What is my lambda? It's a hyperparameter that is set outside the problem, right? So bigger the lambda, what happens? More is the importance of the penalty. So the W will get penalized more. So in the extreme case, if if lambda is infinity, what happens? Yes.
All weights are 0.
All weights are 0. Because even if you allow the weights to be like slightly bigger than 0 or smaller than 0, because it's a norm, so it doesn't matter. Even if you allow it to fluctuate away from 0 even a little bit, this thing will cause this lambda is infinity. So it doesn't matter what the data fit looks like, it will penalize it very harshly. And we want to find a W that minimizes this cost function. Right? So bigger the lambda, the smaller is the norm of W that is outputted from here. Right? And so these two things balance what is the violation of constraint that is allowed, right? Versus how good the data fit is. On the other hand, in constrained optimization problem, we are saying there are no violations allowed. It's a hard constraint. Even if it violates a little bit, just remove that W from consideration. That's what you're telling the optimizer. Right? So one way to look at how the support vectors come about is to convert the constrained optimization problem into a regularized optimization problem. And the way to do that is writing something called the Lagrangian function. Have people seen Lagrangians before? You have seen it. In which course is that? You don't remember, you just like, okay, okay. So if you have taken some other course, I'm not saying you should, that's why I'm talking about it, and that's why I'm taking so long to talk about it. Okay, there's no eraser? Oh, there it is. So in general, I have an optimization problem like this, subject to the constraint gx is less than equal to some 0. I can write down the Lagrangian as f of x plus lambda times g of x. Right? And then I solve, so the Lagrangian is in 2 variables. Then I solve the Lagrangian by minimizing over x and maximizing over the lambda. So essentially, and then you can flip these around, and then you can say that in many cases, solving for one and then solving for other, or solving for the other and then solving for one, tend to be equal. And that is called strong duality. In SVM that holds. In general, there are other classes of F and G where that holds. So what this does is this creates something called a saddle problem in optimization, where you are minimizing over a certain x over one variable. So you're minimizing over one and maximizing over the other. So it creates sort of a saddle. And how do you minimize or maximize? I think we talked about this before. You take the derivative, set it to 0, right? And then you check for the second derivatives, right? So when you take the derivative with respect to lambda here, you will recover the constraints. And when you set it to 0, you will find the best possible value of lambda. So in the constraint set here, you don't want the constraints to be violated. So this will find x that violates no constraints, right? This, on the other hand, is saying I'm going to allow for violation of constraints, right? That's what regularization means. But find me the biggest possible value of lambda so that I penalize it enough so that essentially no constraints are violated. Does that make sense? And if that is where this is called strong duality. So if you search for This is actually the whole duality discussion is a separate lecture. We'll not go deeper into duality in SVMs. If you want to learn more, yeah, sure, you can do online searches. But what this is saying is sometimes we can convert a constrained optimization problem into a regularized optimization problem and then find the lambda where the regularization problem, the answer that it gives you, the x star here, regularized, and x star here, constrained optimization problem, they are equal. Right? So when we were having the discussion about least square L2 regularization, I said it is balancing what? Data fit and the norm of W. But I can equivalently say find me a W whose norm is less than or equal to some C. Right? Instead of having a regularized problem, I could have a constrained problem like this. And then there will be some value of lambda for which this holds. Right? So this is saying I'm allowing the violation of constraints, but I'm maximizing the possible value of lambda, so that find me the best possible lambda for which the regularized problem actually converts to a constraint problem. So penalize it enough so that essentially none of the constraints are violated. Does that make sense intuitively, right? Please ask questions if it does not. Great. So that is the conversion, and like I said, it will find the best possible lambda which barely allows violation of constraints. And what barely means, it means that it will lie on the boundary. So where these constraints will be violated, not violated, it will be right at the edge of almost violation, will be at the support vectors. So when we are writing it as the constrained optimization problem like this, the xi for which this inequality will be equality will exactly be the xi which are the support vectors. Because there the constraints are being satisfied in a hard way, right? That's the inequality becomes equality for exactly the data points which are support vectors. And all of the data points, it's going to be actually a strict inequality. It will not be greater than or equal to, it will be greater than. Okay, great. So we have talked about separable data. What if the data is, I mean, that's, like I said in the beginning, that's a very harsh assumption. That's a strong assumption. What if the data is not separable? So let's say there's a red triangle right on the other side of the pixel app that we picked. So does that mean that SVMs, we cannot use the SVMs there? No, the idea is that instead of saying that we are gonna satisfy all the classifications with some margin in the training data, we say we're gonna satisfy all the correct classification in the training data with margin and some slack, minus some epsilon I, which is what we call slack. And then what we do is when we write down the optimization problem, so this will measure the error, and if this lies between 0 and 1, if it is exactly 0, that means it's actually there's no slack. It's correctly classified on the correct side of the rightmost rightmost or leftmost side of the plane. If it is between 0 and 1, it means that, for example, here this red triangle will have slack between 0 and 1. Right? If it is on the other side, it will become negative. Right? If this red triangle is so far off on the wrong side, it will have slack greater than 1. Right? Make sense? Great. So now we do the same thing that we did for the least square case where we are regularizing. So we are going to balance the minimization of W, which is the maximization of margin, with also minimization of total slack. which are those psi's? Those are supposed to be epsilon. So psi and epsilon are the same. Right? So instead of saying just find the thickest slab, it's saying find the thickest slab and try to minimize the misclassification, which is conceptualized by that epsilon, and then you balance the two with some c, which plays the same role as lambda for the L2 regularization or L1 regularization. Right? So correspondingly, so this is the overall the same thing. So you can write the slack, because it can be written like this. It's if it's correctly classified, there is no slack. If it is already negative. On the other hand, if it is not being correctly classified, the slack will obviously look like this. This is the misclassification error. So how much is the slack is max of 0 and then misclassification error. 1 minus misclassification. And that gives me a new optimization problem, which is written like this. And finally, this thing is also called the hinge loss, in case you decide to read up on your own. So this is saying find a balance between the hinge loss. Hinge loss is the total loss of the total sum of slacks and the margin, which is the minimization of W, subject to the misclassification constraints. But here, because you have essentially taken the misclassification errors directly into the loss, you have converted the constrained optimization problem to a regularized optimization. So you don't need to spell out the constraints separately, because if there are misclassifications, that will go directly into the hinge loss. Great? Okay, thank you. I'll stop.